Hi, my name is Jody Barnett.
I'm Gabe Gallagher.
My name is Sergio Gonzalez.
Hi, my name is Igor Donaldson.
This is our presentation for our capstone on Open Energy Dashboard database optimization. Open Energy Dashboard is a software that a number of different people use, generally for tracking energy usage across a large number of sites. So an example of those sites could be universities. Generally, universities I think is OED's biggest client. It's open source, meaning anyone can work on it under its public license. So we were brought on to help work on it. And generally, OED is a relational database with a graphic user interface that allows its users to collect and track energy usage data for its sites, mostly reading off of like electricity meters for that purpose.
OED currently uses materialized views to handle energy calculations. As the system transitions to support time-varying conversions, where conversion rates can change over time, the computational complexity increases significantly. Supporting time-varying conversions, where rates can change frequently, requires splitting readings into smaller intervals, such as 15 minutes, and significantly increases processing demands. As data grows, these materialized views become slow to refresh and query, which is what motivated us to look for a better solution. Our project objective was to evaluate whether timescale DB could be integrated into OED as a replacement for the current materialized view approach. OED's database handles large amounts of time series energy data, and as that data grows, the current system becomes increasingly slow to query and update. We wanted to determine whether timescale DB's hypertables and continuous aggregates could improve query performance, reduce the overhead of refreshing views, and support time-based queries more efficiently, all without breaking the existing functionality that OED relies on.
DB is a Postgres extension specifically designed for time series data. It uses hypertables to partition readings by time, making queries faster. It also uses continuous aggregates to maintain updated summaries without needing to fully recompute large views every time. This fits well with OED's time-based energy data and aggregation needs. In the current OED system, raw readings are stored in a regular table and queries require a full scan of materialized views, which is slow and resource intensive. In our optimized approach, raw readings are stored in the timescale DB hypertable, and continuous aggregates maintain updated hourly and daily summaries. When a new data comes in, updates automatically propagate to the aggregates without requiring a full recomputation. To implement this, we first updated the Docker database image to a timescale DB-enabled PostgreSQL version. We then enabled the timescale DB extension in the database, created hypertables from the existing reading data, and built hourly and daily continuous aggregates using SQL.
Challenges we ran into with regards to implementing timescale DB before we even found out that it was a solution were the complex code base and data pipeline. So we had to do a lot of code analysis to figure out where the weaknesses were that we decided how to solve, and then we eventually came to decide that timescale DB could solve a number of these code issues. This implementation wasn't easy, and we had to do a lot of testing and benchmarking on the old system and the new one to see how they compared to each other. We eventually did learn from our research that while timescale DB solves a lot of issues for OED, it can't inherently fix schema design problems that OED may already have. Another issue that we ran into while we were talking with our mentor Steve was that real world results may not match our results on test data, but they were thankfully promising enough that OED has decided to move forward with what we've decided to implement and put new developers working on our code with our documentation of the issue. So let's talk about some of those metrics that we found. If we look at our performance results, we ran benchmarks across 3 different date ranges, that being 1 week, 3 months, and 1 year. The left chart here compares the readings table against the hypertable for raw scans. The hypertable did have higher planning time, but significantly lower execution time. The top right chart shows materialized view performance with execution times ranging from 21 to 26 milliseconds. The bottom right shows the continuous aggregate performance with execution times well under 6 milliseconds across all date ranges, which is a dramatic improvement.
What did we actually find? When we compared timescale DB against OED's standard setup, the results were pretty clear. First, just switching the hypertables improved raw scan performance on the reading tables, and that's before we even added the continuous aggregates. The bigger win came from the continuous aggregates themselves. By pre-processing hourly and daily summaries ahead of time, query execution times drop significantly, especially when querying smaller time ranges like a single day or week. The takeaway there is that the more targeted the query, the more dramatic the speed up. Essentially, we move the expensive computation out of the query time and into the background, so users aren't waiting on it. Bringing it all together, TimescaleDB is compatible with OED, and it does meaningfully improve performance. The continuous aggregates were the standout feature. Instead of OED recomputing everything from scratch every time, the hierarchical structure means only new data gets processed. That scales well as the dataset grows, which is exactly the problem OED is facing. There were challenges. The code base is complex, and TimescaleDB isn't a silver bullet for schema design issues, but the performance metrics were promising enough that we're confident this is worth pursuing. Our recommendation is that OED seriously considers integrating TimescaleDB as a long-term solution, particularly as it expands to smaller time intervals and larger datasets. Thanks for listening.